So nucleophile strength is a really important topic in organic chemistry. It tends to come up a lot. A lot of reactions involve negatively charged things as nucleophiles. Again, our definition of a nucleophile comes from the term nucleus loving. So something generally with a negative or a partial negative charge that has a lone pair of electrons that can donate and seek out and form a bond, right? So we use that a lot in organic chemistry. A lot of different examples of that. So periodic trends are real important for nucleophile strength. And so I've got some simplified anions, right? So any carbon with a negative charge or any nitrogen or any oxygen tend to act pretty similarly. And then the series of halogens we see as negative charge as well. And the trend in nucleophile strength goes as atoms get smaller, and then as they get closer towards carbon, aka we're talking about things that are less electronegative, the nucleophile strength increases, right? So you've got your stronger nucleophile on the left, then it gets weaker, and then weaker as you go down. Right, so the strongest nucleophile here on the board is carbon with a negative charge. It's actually very hard to make, whereas iodine or iodide anion, I- is a really weak nucleophile. And of course there's some changes there. It can depend on solvent. There's lots of different things that can adjust these, but this is the basics, right? So why is that the case, right? So it generally tends to come down to two things. What's the electronegativity of the atom with the charge, and what is the size of the atom with the charge? Because that can change the way those electrons interact. So start with electronegativity. For an anion, as it gets less electronegative, right, less pull on that nucleus from the electronegativity, it's generally less stable, right? So the more electronegative atoms are more stable and weaker nucleophiles, right? So that works from left to right for atoms that are around the same size. And size effects is a little bit different. So as we go down, as they get larger, the larger atoms are weaker. Weaker nucleophiles in general, right? So why is that? Why is the size effect? It's not related to the electronegativity quite so much. And it tends to come down to concentration of charge, right? And this works for a lot of different atoms. If you're comparing fluorine, F minus, and bromine, Br minus, right? So they both have one extra electron, so they both have a negative charge. One is a lot larger, right? So my electron shell in fluorine is fairly small, and bromine is pretty big, right? So that extra electron in fluorine doesn't have as much space to fill up, right? So this is going to have a relatively higher concentration of charge, right? So that one extra electron is packed into a much smaller space, right? So it's going to be much more available to find and react. Whereas bromine, still, it's the same -1 charge, but that electron is in a larger electron shell, and thus that extra negativity is a lot more spread out. Right, so the negative charge is more spread out there. And that's a real key thing in organic chemistry and charge stability. You can make a lot of predictions based on how spread out your electrons are, because the more we spread out those electrons, the more stable they are. This comes into play with a lot of explanations like inductive electron withdrawal and resonance. But in general, the more you can spread out the electrons in a system, whether it's charged or not, usually the more stable it's going to be. So your nucleophiles are weaker because that charge is way spread out, right? As you go, if they're all the same size, same amount of spreading, as you go to the left, it's less electronegative, right? Less protons to hold onto that charge, it's much less stable. You gain a lot more stability by bonding there than you would be with bonding fluorine. Right? So you can use this to predict a lot of different nucleophiles in organic chemistry.